So thank you everyone for being here. So today I'm going to be talking about eclipse mapping with Ariel, and in particular, future prospects for a population level mapping survey. So for anyone I haven't met yet, my name's Daniel Valentine, and I'm a final year PhD student at the University of Bristol, where I work on eclipse mapping of exoplanet atmospheres. And what I'm particularly interested in is population level mapping studies for a data-driven approach to understanding the diversity of exoplanet atmospheric dynamics. So let's start off with, how do eclipse observations actually work? So before eclipse, we measure the emission of both the star and the day side of our tidally locked planet. Then during eclipse, we only measure the emission from the star. So by differencing these, we isolate the emission from the planet, allowing us to measure its temperature. But traditionally, we treat the eclipse as essentially instantaneous. So what we actually derive here is a hemispherically averaged approximation of the planet's true temperature profile. But now with eclipse mapping, we can unlock the true 3D profile. So we know that in reality, the eclipse is not an instantaneous process. During ingress, the host star actually gradually occults the planet, leading to gradual flux decreases in the light curve until the planet is fully eclipsed, and vice versa during egress as the planet is revealed from behind the star. And thanks to the high cadence of JWST observations, we actually take many measurements during these times of partial eclipse. So if we know the orbital parameters of the system, then we can calculate the area of the planet that has been newly occulted between each measurement and attribute the difference in flux in that time as having been emitted by that region. So that allows us to build up this slice profile of the atmosphere, essentially mapping the planet in longitude. So we're already at a point now of better than hemispheric resolution, but we can take this technique one step further again. So we get a slice profile across the planet from both ingress and egress, the directions of which are complementary to one another due to the opposing geometries that the stellar limb slices over the planet at those times. So by combining these, what we end up with is a grid that slices over not only the longitudes, but also the latitudes, allowing us to construct a two-dimensional map of the planet's dayside emission profile. And this map is further extended to 3D with spectroscopic observations, wherein different wavelengths probe different pressures in the atmosphere. So by exploiting eclipse geometry, eclipse mapping is currently the only method that is actually capable of doing this. And thanks to the quality of JWST light curves, we've finally been able to apply it to a growing number of targets, which has allowed us to understand the multidimensional atmospheric dynamics in ways that we've never been capable of before. But while we can map the dynamics now, a problem arises when it comes to interpreting them. And that's because, even at first order, these dynamics are governed by a number of parameters that have degenerate impacts on the resultant thermal profile, including the planet's irradiation temperature, its rotation rate, its gravity, and its metallicity, etc. So what this means is that with maps of individual targets, we can't disentangle the effect of each parameter on the atmosphere. To do that, we need a large enough sample size to be able to hold all but one of these parameters in control in order to then isolate the sole impact of the one free parameter on the dynamics. So in short, shock, an observer asking for more data, we need a population level mapping survey, the likes of which JWST is just too time limited to facilitate. So what we need to do this is a dedicated exoplanet mission like Ariel. So for those that don't know, Ariel is an ESA mission set to launch in 2029 to perform a census of about 1,000 transiting exoplanet atmospheres, with constant simultaneous wavelength coverage from zero point 0.5 to 7.8 microns, all of which make it a perfect candidate to facilitate a population level mapping survey like this. So in my most recent paper, I provided an assessment of Ariel's eclipse mapping potential to determine whether it could bring this survey to reality, and join JWST as part of the eclipse mapping world. So to test Ariel's mapping abilities, the natural first step was to take all of the published JWST eclipse maps, with the addition of this HD209 simulation in the bottom left for completeness of the canonical hot Jupiters, and use them as test cases in order to directly benchmark Ariel's mapping abilities against those of JWST. And what we're going to do is use these test cases to answer the following questions. So firstly, will Ariel have eclipse mapping capabilities in the first place? And if so, how many observations will be needed, and how will this compare to JWST? Thirdly then, how expansive will Ariel's mapping abilities be in terms of both the number of targets and the best ways to observe them? And then, finally, what should Ariel's primary mapping focus be with this survey? So what we want to do is take these test case maps and simulate them as we would observe them with Ariel. So the first step is to determine which Ariel spectrograph is the best match for the original JWST spectrograph that was used to obtain the map. So for MIRI LRS, that's AIRS channel 1. For NearSpec G395H, that is AIRS channel 0. And for nearest source order 1, it's Ariel's NearSpec instrument. And then what we want to test is how many observations compared to JWST do we need to recover the same mapping model? And how do the quantitative constraints compare? And there are two quantities of interest that we'll be comparing our constraints on. So the first is the day-night temperature gradient, which we use to diagnose the efficiency of the circulation regime, where the steeper the gradient, the more inefficient the recirculation, and vice versa. The second then is the hotspot offset, the direction and magnitude of which diagnoses the dominant dynamics that are responsible for recirculating this heat. So in this map, for example, we have a small eastward hotspot offset, and that reveals the presence of a fairly temperate equatorial jet dominating the dynamics. So as you can see together, these two mapping observables provide essentially a first order characterization of the atmospheric dynamics. So these are what we really want to test Ariel's ability to measure. So to carry out our test cases, what we do is we take our input JWST maps, extract the eclipse mapping signals from the light curves, simulate them as they would be observed using the equivalent Ariel spectrograph, and then retrieve the equivalent map as it would be observed with Ariel. Okay, so let's now use these test cases to address each of our questions in turn. So starting off with, does Ariel have eclipse mapping capabilities in the first place? Well, the perfect test cases to answer that are 189 and 209, because as our brightest and highest ranking mapping targets, if Ariel can't map these, then it can't really map anything. So here are the maps as we observe them with JWST, and then these are the equivalent maps that we derive with Ariel. And we are actually able to derive these in the same observing time as we were able to with JWST. Now, by differencing these two maps, we can assess how well Ariel is able to recover the input. And as you can see from the similarity of the JWST and Ariel maps and the flatness of the difference maps, Ariel is able to accurately recover the injected thermal structure for both of these highest ranking targets. And in terms of quantitative constraints, we recover our two key mapping parameters, so those being the temperature gradient and the hotspot offset, at around a half to a third times as good precision with Ariel as we do with JWST in the same observing time, which is a really encouraging result given that Ariel is a much smaller telescope, more than 6 times smaller than JWST. So the answer to our first question is that yes, Ariel can map bright, high-ranking mapping targets in the same observing time as JWST can. Okay, so now that we know that Ariel does in fact have eclipse mapping capabilities, we move on to question number 2. How does it compare against JWST? So for our best and brightest targets, Ariel could derive the map in the same observing time as JWST could. But what about for a dimmer target now? Ariel will probably need more data, but how much more? And the test case that we'll be using to answer this is WSP18, which is about 2 to 3 orders of magnitude dimmer than 189 and 209. So it's unsurprising that in this case we require more observations with Ariel than we do with JWST in order to recover the input map. But we find that with just 3 times as many observations, Ariel is able to accurately and precisely recover the input map and actually match JWST's quantitative constraints on key mapping observables like the temperature profile. And while asking for 3 eclipses on the JWST can be tough, Ariel is a dedicated exoplanet mission, so 3 eclipses is more than feasible for a single target. So the answer to this test case is that Ariel's greater dedicated observing time will enable it to compete with JWST for dimmer targets using as few as 3 times as many observations. So motivated by this result, we now move on to our third question. How expansive will Ariel's mapping abilities truly be? So we've just shown that with a feasible number of observations, Ariel will be able to map many of our brightest targets. But will it also be able to map the dimmer ones, which we'll need to include if we're going to build up a population level sample? And the test case that we'll use to answer this is WSP17, which is another 2 orders of magnitude dimmer than our previous test case. But despite the dimness of the system, we were able to map it with JWST using just a single eclipse observation, thanks to JWST's ultra-high precision. So with this test case, we're really assessing how comprehensive the smaller aerial telescope's mapping abilities will be. So unsurprisingly, we need yet more data again to recover the map in this case, but the amount is still not excessive, with Ariel still able to recover the input mapping model using only 5 times as many observations as JWST. But whereas for our previous test case, we recovered the input map at the same quality as JWST, the map in this case is recovered with both poor accuracy and precision, as evidenced by the large degree of residual structure in the difference map and the much larger uncertainties on our key mapping parameters. So if we try upping our number of observations now to Ariel's upper limit per target of 20, then Ariel starts to better compete with JWST, but it still can't quite match its constraints, and nowhere near well enough to justify using 20 times as much observing time. So the unfortunate conclusion here is that for dimmer targets, Ariel cannot compete with JWST using eclipses alone. But the key wording here is that using eclipses alone. So that tells us that the solution here is actually just to change our observing style. In particular, instead of only using eclipses, to use phase curves. Because adding in this phase information as the planet rotates on its orbit tells us a lot about the longitudinal profile of the atmosphere. So combining that with what we get in ingress-egress gives us a second independent constraint on the thermal profile, leading to much better constrained maps. And while asking for a full phase curve of a 4-day period target like WST-17 would be nigh on impossible on JWST, a dedicated exoplanet mission like Ariel is more than capable of doing this. So using a phase curve to map WST-17 now, we see that we much more accurately recover the input map, and our constraints on both the temperature profile and the hotspot offset are much tighter, even surpassing JWST at this point. And this is in fact the most cost-effective way to map these lower-ranking mapping targets with Ariel, amounting to half the observing time compared to using eclipses alone, and yielding much better constrained results. So the main conclusion from this test case is that by using phase curves, Ariel can also map dim targets. And in fact, phase curves are the most time-efficient way for Ariel to map them, which will enable it to carry out the population-level mapping survey that we seek to conduct. So this then moves us on to our final question. What should Ariel's primary mapping focus be with this survey? So up until now, we've shown that Ariel can map the longitudinal profiles of all of our test cases. But as I said earlier, Eclipse mapping can also uniquely map the latitudinal profile. So how does Ariel perform in that regard? Well, the perfect test case to answer that are our two WST-43 maps, which show latitudinal hotspot offsets of about 10 degrees south in both maps. So what's the significance of this? Well, longitudinal signals are present in the entire phase curve, whereas latitudinal signals are localized to ingress-egress and tend to be much smaller amplitude, making them much harder to measure. So we're really pushing Ariel's mapping abilities to their limits here to see whether it can also recover them. And the answer is that yes, Ariel can still recover them, but is it worth it? So whilst Ariel can accurately recover both the longitudinal and the latitudinal signal here, and at the same precision as JWST, it requires 18 phase curves compared to JWST's 1, and this is true in both bandpasses. So even for a dedicated exoplanet mission, this amount of observing time for a single target is starting to become unfeasible, surpassing 15 days. But since latitudinal signals are localized to ingress-egress, can't we just observe 18 eclipses instead? Well, no, because in that case, we actually don't recover the latitudinal signal because we need the phase signal to anchor the longitudinal profile and disentangle those signals from the latitudinal ones in ingress-egress. So this 15 days really is the bare minimum observing time that we would need with Ariel to recover these signals. So the answer to this test case is that yes, Ariel can do small scale and latitudinal signals, but not easily. So those are better left to larger observatories like JWST, because that's where JWST's strengths lie, in its data quality. What Ariel should instead focus on is where its strengths lie, and that's in its data quantity. So we showed with our previous test cases that Ariel will have the ability to map the large-scale longitudinal profiles of targets spanning several orders of magnitude in brightness. So what should Ariel focus on with this survey? Well, it should just focus on what it does best, which is measuring these signals for a large number of targets. Because by measuring their temperature gradient and longitudinal hotspot offsets in this way, we can still constrain their first-order atmospheric dynamics, which, with a sample of this size, will allow us to break the dynamics degeneracy that I posed earlier and achieve that demographic understanding of exoplanet atmospheric dynamics that we're after. And as we've shown, for Ariel to map a large population of planets like this, the best and most time-efficient way is through the use of phase curves. So now that we know that Ariel can do the survey and how it should do the survey, the next question is, what is our target list? Well, to determine that, we can use the aptly named Eclipse Mapping Metric. So these equations look quite complicated, and don't worry, they are. So I'm not going to get into the derivation of them here. But in simple terms, all the EMM really is the minimum resolution element that we can map a planet to. So a value of less than 90 degrees means that we can map the planet at better than hemispheric resolution, making it eclipse mappable. And as you can see, this metric carries dependencies for all the parameters that we might expect to affect whether a planet is mappable, including the measured flux, which carries the system brightness and planetary temperature dependence, the flux error, which carries our precision and cadence dependence, the impact parameter of the orbit, the semi-major axis of the orbit, and the planetary radius, the combination of which carry the dependence of the eclipse geometry and ingress-egress duration. So using this metric, we find that, with our proposed observing strategy, Ariel will be capable of mapping 138 targets using at least 1 out of 3 of its spectrographs, which is a great result for our population-level survey needs. But the question now is, how long would it actually take to observe all these targets? And the unfortunate answer is too long, about 60% of the mission lifetime. So what we clearly need are some selection cuts. Now, the first thing that we can do is enforce a constraint in order to maximize the scientific returns of the survey, and that is removing targets that are only eclipse mappable in 1 out of 3 of the spectrographs. So by enforcing this, we're still left with 112 targets that are mappable in at least 2 out of 3 of the spectrographs, and these now only take 42% of the mission lifetime to observe. So still a bit too long, but getting better. The next selection cut that we can then look at is the time efficiency of observing each target. So in the bottom right here, I'm plotting in blue the number of observable targets as a function of their maximum period. And then in red, I'm plotting the percentage of the mission lifetime that would be required to observe those targets. And straight away, we can see that these curves plateau at a period of about 6.4 days. So by enforcing a period cutoff at this value, we only lose the 3 long period targets to the right. And just from dropping those 3, we shave off another 4% of the mission lifetime from our survey. So what this shows is that for time efficiency, what we clearly need is a period cutoff. And we can actually see that there's an even earlier reduction in the time efficiency of the survey in the form of a step function at about the 4.2 day mark. So if we now adopt this as our period cutoff, then that still leaves us with 87 targets. And these are now observable using only a quarter of the mission lifetime, which is in line with the expected phase curve budget for the Ariel mission. And in terms of demographics, we can see that none of the targets in the yellow region provide any significant added diversity to our sample beyond period, compared to the more efficiently observed targets that we have in the green region. So we really don't lose anything by dropping these targets from the survey, but we save a hell of a lot of observing time. So by adopting this 4.2 day period cutoff as the second criterion of our survey, we are therefore focusing on a survey of short period targets, but for which we can observe entire phase curves of 87 of these using only a quarter of the mission lifetime. And in terms of demographics, we can see that these 87 targets span a wide range of periods, irradiation temperatures, planetary radii, masses, and gravities. And if we think back to the parameters at the start of the talk, I said to generally impact atmospheric dynamics and how they correlate with the demographics of our survey, then we can see that a mapping survey of this size and diversity would therefore enable us to break these degeneracies and finally determine how each parameter individually influences the dynamics. And in terms of scale, this survey would surpass the previous largest attempt using Spitzer by a factor of 3, which really just highlights Ariel's potential to truly revolutionize our demographic understanding of exoplanet atmospheric dynamics. So in summary, our key takeaways are that Ariel can map high-ranking targets using the same amount of observing time as JWST. It can map mid-ranking targets using as little as 3 times the observing time required by JWST, And it can in fact map all of our targets, including the dimmest, by using phase curves. And while Ariel can't quite match JWST in terms of measuring latitudinal signals very easily, it can quite easily map the longitudinal profile of more than 100 targets and constrain their first order atmospheric dynamics. So the conclusion is that Ariel is in fact capable of conducting a population level mapping survey. And the best way to conduct this is by using phase curves, which we can acquire for 87 of the best mapping targets with periods of less than 4.2 days using only a quarter of the Ariel mission lifetime. And with that, I'll invite any questions that anyone might have.
Thanks, Dan. That was a really great talk and a very well mapped presentation as well.
Thanks.
If anybody has any questions, please feel free to ask. Yeah, Anna.
Right. Very well made presentation. You talked a lot about the div, like what you gain by several eclipses. Do you also gain more by using different like the different instruments on a single target? Would that help you, or would it be better to just increase the precision by using the same instrument over and over again?
Yeah, so one really great thing about Ariel is that it simultaneously observes using all of its instruments, whereas JWST only observes with one at a time. So with Ariel, we always naturally observe all the way from zero point 0.5 to 7.8 microns. Now, because those wavelengths are going to be probing different pressures in the atmosphere, we can't really combine them in order to increase our mapping signal. But what it means is that we inherently essentially get 3D maps out of our data, whereas with JWST, we're kind of usually only fixed to one pressure level. So that's kind of why we need to look at using phase curves in order to increase the precision of our mapping signal. But with Ariel, we really get a lot more information than we get with just a single observation with JWST.
Any other questions? I have a quick question, Dan.
Hmm.
Can you tell me a little bit more about the sort of process of simulating this from JWST to Ariel?
Yeah, sure. I think I have a backup slide for this. Yeah, so essentially what we do is we take the JWST Eclipse maps and then we use the Starry software in order to simulate the aerial maps and inject that mapping signal into the light curves. And then when we're actually doing the light curves, we're simulating the cadence and precision of our observations using the aerial rad tool. So that's essentially the aerial version of Pandexo. So it does like a full noise model simulation of a true aerial observation. So that's how we go about creating our simulations. And then we use the Teresa eclipse mapping code in order to then fit those light curves and then extract the eclipse maps at the end.
Great, thank you. Any final questions? Yeah.
This was a great talk. I was wondering, the precision, I guess is photon noise limited here. That's the assumption, or if not, have you looked at what kind of survey sample you could have if, say, the performance was worse than anticipated a little bit? Have you looked into that?
Yeah, so these are photon noise limited. We've not accounted for any like systematics or anything yet in the data because before, full space-based tests, we don't quite know how the aerial instrument is going to be performing, but those are added simulations that we're going to want to do kind of closer to the mission launch in order to determine, in a more pessimistic scenario, maybe how many more observations we need for each target and how that might limit the sample size then.
Okay, thanks.
Anna, did you have another question?
And just a very final quick one. Uh, your curves are super smooth. Are you anticipating or even hoping to even also see the stellar activity within your phase curves if you scan the whole phase curve?
As in, Are we hoping to see stellar activity?
Yeah, as in you can map it if you have that long of a baseline.
Yeah, so that's actually one part of why I'm advocating for using full phase curves, because really, if you want to do the eclipse mapping of the day side, you only really need to extend your baseline around eclipse. But while that's great for us, it doesn't really help the community as a whole. But with a full phase curve, of course, there's so much more ancillary science that you can do, mapping the global profile, mapping the night side, looking for stellar activity. So that's kind of why, in the interest of like the aerial mission ethos, phase curves are probably like the most advantageous strategy in order to help everyone achieve their aims. So yeah, that would be a really cool thing that we could do with this phase curve survey as well.